Okay, we are back. Let me explain why BSang 3D IC will be crucial to the semiconductor industry. The semiconductor industry is facing fundamental limitation in device size shrinking, lithography tools, and return on investment. Device shrinking in lateral dimension based on Moore's law has been continuing for the last several decades. For example, cost per bit for memory devices has been the most important priority, and it is continuously decreasing through the device size shrinking. However, many people are talking about the end of device shrinking. As an example, it seems very uncertain if DRAM can be manufacturable at or under a low 20 nanometer technology node, which is just 1 or 2 steps away from the technology node currently in mass production. The rapid increase of COO, or cost of operation, and delay of EUV or extreme ultraviolet tools are also important limitations of semiconductor innovation. As seen in this graph, the cost of lithography tools exponentially increased in the last several decades. According to VLSI research, the cost of pre-production level EUV already hit $125 million. However, the throughput of EUV is far away from production level yet, and there are still many technical challenges associated with EUV. In the meanwhile, immersion lithography tools should be used for small geometry devices. Double patterning or quadruple patterning with immersion lithography tools abruptly increase the operating cost of lithography tools for mass production. Here is a chart of technology node and total cost per layer. At 90 nanometer node, the tool cost was $10 million. However, it becomes $50 million at 50 nanometer node. For 30 nanometer node, tool cost per layer goes up to $150 million with double patterning. If quadruple patterning is needed at low 20 nanometer node for DRAM, the total cost per layer will be at least $300 million. The total cost associated with double patterning with EUV at 10 nanometer node might be the same even though EUV is available at 10 nanometer node. How much investment in lithography tools are needed for a mega fab? Due to the high manufacturing costs associated with lithography tools and low return on investment from fab, some semiconductor companies need 450 millimeter wafer fab in order to reduce die cost and therefore increase ROI from fab investment. The estimated price tag of a 450 millimeter fab is about $10 billion. It is too much for most semiconductor manufacturing companies. Lack of support from tool companies for 450 millimeter manufacturing is another issue. It is interesting to measure the value of $10 billion and what we can buy with $10 billion. Semiconductor companies are facing the toughest challenges they have ever met. I believe BSang 3D IC is an ultimate solution for these toughest challenges. BSang is a pioneer in 3D IC and has developed 3D IC technologies for the last 8 years. BSang has not only numerous foundational intellectual properties and also developed its proprietary 3D IC technologies by experienced internal engineering teams. BSang 3D IC has been implemented at Stanford NanoFab and again demonstrated at commercial level technology in 2008. BSang keeps pushing its disruptive 3D IC solutions development for various applications. I would like to mention that BSang is the only company which has accumulated experience and practical solutions for true 3D ICs. Okay, it's time to explain BSang's true 3D IC. Here is a simple process flow of BSang's 3D IC. It starts from an acceptor wafer with conventional devices on silicon surface and interconnect regions with aluminum or copper wires. In the meanwhile, another wafer called a donor wafer is prepared. The donor wafer has impurity junctions and a detaching region. Then the acceptor wafer and donor wafers are bonded face to face. After wafer bonding takes place, the substrate of the donor wafer is separated along the detached region. Using the transferred device layer where impurity junctions are already formed, vertical transistors are formed through pillar etching. These pillars work as MOSFETs and provide high-performance device functions for various applications. Vertical pillar transistors are just one of many transistors or other device forms which could be implemented using BSang's 3D IC. Planar MOSFET, simple diode, capacitor, bipolar junction transistor, sensor, and many other devices could be formed on this transferred 3D layer. In this presentation, I'd like to explain the details of BSang's 3D IC based on vertical transistor as an example. Low temperature processing is essential for true 3D IC. All processing temperatures of BSang's 3D IC remain below 400 degrees Celsius in order to avoid disturbing or changing existing underlying devices and metal lines in the interconnect region. If the 3D IC process disturbs existing underlying devices, complications due to 3D IC design will quickly rise and yield will drop down sharply. In order to realize true 3D IC, low processing temperatures are an essential requirement. Defect or damage-free single crystalline silicon formation is needed on top of the wafer where devices and metal interconnects already exist. For high-quality device and high yield, defect-free material formation is very important. Again, semiconductor material is an extremely important matter. There have been and still are many trials done in the search for new material that will eventually replace single crystalline silicon. So far, however, no new material or polysilicon can be closely compared to single crystalline silicon in terms of quality, reliability, device density, and device performance. Emerging memories based on emerging materials such as resistive RAM and phase change memory demonstrated 3D cell stacking capabilities. However, these emerging memories should demonstrate competitive cell density compared to silicon-based memory cells. Otherwise, the meaning of 3D stacking cell would be diminished. Many companies are also working on 3D stacking NAND cells using unusual combination of polysilicon, metal, and other materials. However, I believe the main issue associated with these 3D NAND stacking cell is the unusual combination of materials.